put up a few pictures of people who are important for colloids. So you might recognize this guy, Herman Schlowinger, who of course is the founding father of macromolecules, of polymer science. And the idea is that we have a flexible object, right? You have a problem? No. Huh? Okay, there seems to be a problem with the auto zoom. I will try not to move as much. Typically it works, okay? So we have Herman Schlowinger.
Okay.
Okay, good, thanks. Herman Schlowinger representing the polymer science. Then this guy is Zsigmondy, who worked on colloids. And you might know this person here, Langmuir, who of course is well known for the Langmuir trough and the interfaces. Well, I put up Agnes Pockels because actually it was her who invented what is now called the Langmuir trough a few years before Irvine Langmuir. Okay, now why do I put these three fields of polymers, colloids, and surfactants here? Because what we're working on is microgels. And now you might also wonder, this obviously is a cartoon. This is a cartoon. This is not a cartoon. This is a result from a computer simulation from Roland Winkler's group in Jülich. And now microgels are somewhat in between all these other three types of colloids. They are swollen as a polymer network. So the surface is like a linear polymer. So it's cross-linked polymer. It's swollen in the solvent. And if we change the solvent conditions such that the solvent becomes a poor solvent, then this swollen network can collapse. And if they collapse, they basically become a latex. They become a regular rigid colloid. Now you could imagine that the structure of these microgels depends on the degree of cross-linking. So if we go reduce the crosslinks, we will eventually come to something like a branched polymer or to the behavior of a linear polymer. And microgels are also interfacially active. They can adsorb to interfaces, and they can form films like surfactants can do. So microgels are a special type of material that can mimic the properties of rigid colloid, the properties of polymers, and the properties of surfactants. And this is what I will talk about in this lecture. Okay, now we are working as a physical chemist. Typically, we like to work with model systems, and we work with a well-developed model system, the N-isopropyl-acrylamide. So it's an isopropyl-acrylamide group. We add a cross-linker. We do a simple precipitation polymerization, and we end up with objects that are spherical particles, right? This is a well-known system described first by Bob Pelton in Canada. And the nice thing is that when we have aqueous solutions of this polymer, then we have phase separation upon heating. So we have a one-phase system at low temperature and phase separation upon heating. And the lower critical solution temperature is about 32 degrees centigrade. So this is the temperature range, which is very nice to work with. And the polymerization leads to very monodisperse objects, which is also very important for our studies. Now, as I said, we do a polymerization by adding a cross-linker. So we end up in the precipitation polymerization with particles that are internally cross-linked. And then when we cool down, they can swell. And so what we have is an object, the size of which depends on temperature. So here we plot the size of the hydrodynamic radius determined from dynamic light scattering, for instance, as a function of temperature. And what we see is that the size goes down. Now, in this case, it goes down by a factor of 2 approximately. So the volume changes by a factor of 8. And this transition is completely reversible. And the system is also colloidally stable in the collapse state. That allows us to probe the collapse state as well as the swollen state. Now, one would like to image those particles. And we have a very nice collaboration with Dominic Wöll, who is an expert in super resolution, super resolved fluorescence microscopy. And this is what one gets from the studies in his groups. And so you see the object coming out, and the color code gives you the number of localizations of the dye that we see. And you see that in the interior, we have more objects. And the further we go out, we have less monomers or less polymer segments that we can visualize. Now, the visualization, of course, is not really the polymer network. It's the dye that is attached or linked to the polymer particle. Now, imaging is nice. We all know that a picture is worth 1,000 words. Well, I've been to Toronto, and they have a museum of illusions, and an illusion is worth 1,000,000 words. And now that's already a big number, but we like to do scattering, because scattering really probes a huge number of objects. And that means if we have scattering data and do understand the scattering data, then we can be really sure that this is representative of the material. When we do imaging with microscopy, we really have to make sure that what we see in microscopy is representative for all the other things. Okay, so we do a lot of scattering in our group, mostly light scattering, of course, in-house static and dynamic light scattering. We also use X-rays and neutrons, and there we go for large-scale facilities, for instance, to the ESIF in Grenoble, or we use the beam lines at the ILL in Grenoble or in Munich, or also at NIST. Now at Imperial College, of course, I don't have to say anything about neutrons and polymers. It's well known and described by Julia in this wonderful book. Okay, so when we do this neutron scattering or X-ray scattering, let me give you a short introduction. What we obtain is the scattering intensity. And the scattering intensity depends on a few things. It depends on the concentration. It depends on the contrast. And then what we are mostly interested in is the form factor, which describes the shape of the object. Now, the analysis we do in close collaboration with Janskov Petersen in Aarhus. So what we typically do is we develop a model in real space. From that, calculate the form factor model, and then fit that model to the data. Yeah, so here we have the scattering data, scattering intensity as a function of scattering vector or scattering angle. Now we do this by taking into account the polydispersity and also the resolution of the instrument. And then when we fit this, when we fit the data with a model, then what we get is what we call the density profile. So this gives us the volume fraction of polymer segments as a function of the distance from the center of the particle. Okay, now for those of you who like equations, this is the equation. Nothing new compared to what I said before. So what do we have? We have the scattering contrast that we can determine independently. We have the instrumental resolution that we can also determine independently. The particle size distribution is typically below 10% in our systems. The particle volume, that is something we want to get. Also the form factor, I will come to that in a minute. The structure factor would give us the interaction between the particles or the microgels. If we go to infinite dilution or to very high dilution, we can neglect the structure factor. Or if we go to higher concentration, we can probe the structure factor. And then when we go to very high scattering angle, to very high Q, we can also look into the internal structure of the microgels at very short length scales. Yeah. Now the point is that it looks terrible. And some people claim that you can fit an elephant with this equation. I will tell you that this is not the case. Huh? Okay, now coming back to our microgels. So when we do the neutron scattering, then what we see is when we have it in the collapsed state at high temperature, we have a homogeneous sphere. Right? Now when we cool down the system and it swells, then what we actually see is, and that is what we see in the scattering, what we also saw in the microscope image, is that the distribution of polymer segments decays smoothly when we come from the inside to the outside. And this is also reflected here again in this computer simulation. So what we have is an object which is rather fuzzy at the surface. Now the chemical reason for that is that the crosslinker reacts faster than the monomer during the reaction. So it's consumed faster and we have less and less crosslinks available the further the particle grows. But the nice thing is it makes this microgel well defined in terms of it's a cross-linked system, a cross-linked object, but the surface is fuzzy. Yeah. Okay, now this is illustrated here. We can use this to make compartments. We can use different polymers. I will show that in a minute. But it also tells us that we have an interesting interface between the microgel and the surrounding. As it's a swollen network, it's permeable, at least for small molecules, and depending on the mesh size, it will be permeable for larger molecules as well. And as it's a gel-like object, it also has the opportunity to adapt to its surroundings, so it can deform. And that makes it different to other colloidal systems. Now I will start with talking about compartments. And the first experiment, the first thing I would like to notice here is that neutron scattering is extremely helpful in these studies because we can easily vary the contrast by changing, for instance, the H2O to D2O ratio in the solvent. And if we have, for instance, a core shell object which has a different scattering contrast in core and shell, as illustrated here, then when we change the composition of the solvent, we will see different regions of the object, of the microgel, for instance. Now, these are core shell microgels with a silica core and a polymer shell. It's the same system at different contrast. And you see that we have a very different scattering function, definitely a very different scattering curve. And we are now able to fit all these curves with one model, just taking into account the different contrast we have. And this gives us quite strong evidence that the form factor that describes these objects is sufficient and is a good model, right? Okay, so I will show you first an example which is a few years old, but is nice in that respect because it combines two different types of polymers. So we start with the well-known polynipam, but we have a second polymer. It's the methylacrylamide. It has a methyl group in the backbone, and that makes it a little bit better water soluble. So it also has a transition temperature, but instead of 34 degrees C, we have 44 degrees C. And now we made core shell particles out of this. And I will go through this plot. What we have here is the size as a function of temperature. And the red curve is the microgel made from this polymethyl polyinisopropyl methyl methacrylate. And it's small, collapses at high temperature, and it swells at around 42 degrees, 44 degrees centigrade. It starts to swell. Okay, now we use this as a seed for a second polymerization. And we polymerize a shell of polynipam. Okay, so the object becomes bigger, the particle is bigger. So now we cool this down. Now the polynipam, which is the shell, does not want to swell at 40 degrees centigrade. So we have now an object where the shell acts like a corset and keeps prevents the core from swelling. And then, so the core shell system, which is bigger at high temperature, is now smaller than the naked core would be. And then when we further go down, it swells totally. Now, and that shows it's important now that the outer layer, the shell, is cross-linked. So it's basically as tight as one swells, the system cannot swell because it has a shell which is still collapsed. Yeah? Now you might argue that my line of thought is not really convincing because what I discuss here is only the outer size that we measure the hydrodynamic radius. Absolutely true, but I can say we have done the neutron scattering data, we have seen the neutron scattering curves, and that fits with the core shell model. So we are very confident that this is really the internal structure as I described before. So now one can use this structure to get even more complex objects of microgels. So we can start with a silica particle, add the polynipam, the polymer with a lower transition temperature, add the polynipam, then dissolve the silica, and then you would end up with a hollow microgel. Now, a hollow microgel that has two polymer layers, which are both collapsed. Now we could cool down. The outer one would be swollen. That's an important point because now the inner shell should be collapsed. Could be a barrier for uptake and release applications. And the outer shell would be swollen, providing colloidal stability. Yeah? And Now we can also go now further down with the temperature. We would swell the inner part. Then we could use this for uptake and release. So you can imagine that it works. Now this is a computer simulation. And we have all the neutron scattering data showing that the computer simulation results are correct. Now I will show you in the next slide a cut through these objects, just to give you an idea what is the peculiar properties of these types of hollow microgels. This is shown here. So this is basically a cut at the equator. This is the core shell system, shell system, and this is the hollow one. So we just put it into 4 quarters. And I would like to draw your attention to the point. So this basically is a different temperature. Both shells are swollen. Inner shell is collapsed. Both shells are collapsed. And I would like to draw your attention to the difference between a system which has only 1 polymer shell or the one that has 2. The fact that we have a second network affects the swelling of the inner network. Yeah? Now, because if you remove the silica core, then of course the network can fill the void, the cavity. But if we add a second polymer layer, that prevents also the swelling of the network to the inside. So basically, this is kind of an inverted corset. Yeah? Now, having these 2 different polymers allows us now controlling the size of the void, the density of the shell we could use, and we can also control colloidal stability. So we have a very versatile system at hand here. Okay, now you could say spheres are boring. Well, we can also go to anisotropic objects. Anne was able to make elongated objects using an inorganic core with an ellipsoidal shape. And then we could make a hollow microgel. It's a multi-step synthesis. And this is electron microscopy. Here you can see the inorganic nanoparticles that are definitely anisotropic. Here, it might already be very tough to see that there is the microgel layer around it. You can hardly see it, but it is. And here, this is what's supposedly the hollow one. Now, the cartoon says it's hollow. In the TEM image, electron microscopy image, you cannot really tell. Now, to make a long story short, we have again the neutron scattering data. And trust me, we fitted the neutron scattering data with many different models. And only anisotropic models that do have a cavity fit the data sufficiently well. And so this is illustrated here. That is with a silica particle where we indexed match the silica so that the scattering only comes from the polymer. And this is the hollow one where the silica and iron oxide core was removed. And we see a different shape. With the silica core, it's more ellipsoidal. Without, it's a little more like a cylinder. I would not go too much into the details here, but we have clearly an anisotropic object. And now you could again imagine that depending on the thickness, it might play a role whether the cavity which comes from the place where the core was removed is filled or not. That indeed is true. If we go to a thinner shell, we can create a much larger cavity inside. Okay, so we have objects where we can make different structures, different compartments, and they are responsive to temperature or pH. Now, is this rather a particle or is this rather a macromolecule? So how can we change the softness? And one idea would be to change, for instance, the crosslink density. Yeah? We could also think about charges. We have done this, but I will not touch this in my talk today. Okay, now for hard spheres, it's well known that when we increase the concentration of hard spheres, they form colloidal crystals, this famous paper by Pusey and Van Meegen. Now, what about microgels? Do they form colloidal crystals? For hard spheres, that transition between fluid and crystalline phase is around 50% in volume. Now, for microgels, they do form crystals, but this is shifted to higher concentration. So we need a higher volume fraction. Obviously, they are soft, and that softness shifts it to higher volume fraction. Now we can control the degree of crosslinking, and we can do something with this polyniper microgels, which is called ultra-low crosslink microgels. These are microgels where we do not add a dedicated crosslinker during the synthesis, but which just self-crosslink. And this is what they call ultra-low crosslink microgels. And you can see here, hopefully in the images, that they also form colloidal crystals at even higher volume fraction. But they do form a colloidal crystal that is different as compared, for instance, to dendrimers, which apparently do not form colloidal crystals. So we would say, they behave like a particle. Okay. Now, when we think about this, when we increase the concentration of these objects, hard spheres can just pack. But if they are soft spheres, they have different options to react to this higher concentration. They could either deswell, they could interpenetrate, or they could deform, like in a foam, for instance. Now, in the literature, there is a debate about what happens. And we were interested in looking into this with our small microgels, where you cannot do microscopy. These are too small to really see them with sufficient resolution in microscopy. Okay, so the idea was we take a normal microgel, we have the monomer and the crosslinker, and then we change it in two ways. One way is that we have less crosslinks. We come to the ultra-low crosslink microgels. The other idea is we make a different architecture. We make a hollow microgel. And what would you predict is softer? I would not predict anything anymore, so I'm always surprised what happens. So what we do now is an experiment such that we use normal microgels, which we call 5% cross-linked, and we add either an ultra-low cross-linked microgel, a hollow microgel, or a similar cross-linked microgel, but the difference here is now that these are deuterated. So when we now do small angle X-ray scattering from these objects, the scattering contrast is basically the same, and what we get from the X-ray scattering is the nearest neighbor distance of these objects. When we do this, we get the nearest neighbor distance as a function of concentration. Okay. So we know how far apart the microgels are. So now we take exactly the same system, but instead from X-rays, we go for neutrons. Because in neutrons, we can index match, contrast match the blue ones here by having a D2O water mixture which has the same scattering contrast. So in neutrons, we only see those microgels, and now we can determine the size and the shape of these microgels. Now, we of course fit the entire form factor. In the following slide, I will just give you one information, which is basically the size. Yeah. Okay, so that slide looks busy, but I will go through it in a minute. What we plot here is the size, and the size could either be, let's say that's the size of the microgel, and this red line here describes the distance between the objects. This is what we get from the X-ray scattering. Okay, now we have looked at probe microgels, ones that are also crossing with 5 mole% crosslinker order 2.5, and that's their size. And what we see is when we increase the concentration, their size is bigger than the distance. And that means they really have to interpenetrate. And so due to the fact that they have these dangling chains and that the crosslinking at the surface is much smaller compared to the crosslinking in the core of the microgels, they are able to interpenetrate. Now, when we do the same experiment with the ultra-low crosslink microgels, or the hollow ones, these are these signs here, that's the ultra-low crosslink, these are the hollow ones, we see that the hollow ones are much smaller. So the hollow microgels and the ultra-low crosslink, they deswell. So the more cross-linked ones can interpenetrate or do interpenetrate, and the hollow ones rather prefer to fill the cavity, to shrink into the cavity instead of interpenetration. That shows us that the architecture plays an important role. Yeah? So a cross-linked, a 2.5% cross-linked hollow microgel is softer in terms of deswelling compared to a 5 mole% normal microgel or 2.5% normal microgel. Okay, now that was we put this microgel into a surrounding of 5 mole% cross-linked particles. What happens if we mix the ultra-low cross-linked with ultra-low cross-linked? That was a little bit more complicated to get them correctly deuterated, to get the contrast right, but that was fine, okay. What we see here is that when we have the ultra-low cross-linked microgels at high concentration, they form colloidal crystals. That was the image we have seen before. And basically, we see some interpenetration and then deswelling. So the size gets smaller. And now there's one important, let's say, important additional aspect. When we do the scattering analysis, we have to increase the apparent polydispersity. And that is a strong indication that the objects are no longer spherical anymore. Yeah? There, of course, is a problem now with the analysis of the scattering. So if we go to very large microgels, one could look at that in terms of microscopy. Now, other groups have done this, and they have seen faceting for large microgels. So we expect that also these smaller microgels, these very soft ones, do deform when we increase the concentration. So that was for the ultra-low cross-link. What about the hollow ones? When we put hollow in hollow ones, the first observation was they do not form colloidal crystals. So instead of packing into a colloidal crystal, as normal microgels would do, or even the ultra-low cross-link microgels do, hollow microgels do not form colloidal crystals. What they do instead is they swell into the cavity. So they rather deswell than forming colloidal crystals. Now that is interesting now because we can now use these hollow microgels to create defects in colloidal crystals. And that is, from fundamental issues, very interesting because we can now look into the process of crystallization. You know that colloids are used as model systems for atomic systems. Now there is no atomic equivalent of a hollow microgel. There is no hollow atom. So we can do now things in soft matter, or let's say, yeah, soft matter crystals, crystallization, which cannot be done with a normal system. Okay. Now, so you see they are different compared to normal colloids, but when we collapse them, they should become a normal colloid. How do they collapse to hard spheres? Well, we wanted to make time-resolved scattering experiments, and we exploited a feature of polynipalm, which is called co-non-solvency. Co-non-solvency means that when we add two good solvents, the mixture of two good solvents is a poor solvent. And that's the case for this system here with water and methanol. So at low temperature in water, it's swollen. In methanol, it's swollen. But in a water-methanol mixture, it's not swollen, it collapses. Yeah? So here we have the size as a function of temperature. Methanol, not temperature dependent. In water at low temperature, it has about the same size. And when we have the solvent mixture, it's collapsed. So the idea was to use a stopped flow device where we mix a microgel solution with a second solvent and then do the time-resolved scattering. We did this at the ESRF, and this is the data. Scattering intensity as a function of scattering vector. And when I saw this, it was blasted. Look at this. 1, 2, 3, 4, 5, 6, 7, 8 minima. Wonderful. It immediately shows us it must be very monodisperse. So I was really extremely happy when we had this data. And then we started to look at the data evaluation, and that became a little troublesome. We started with the first model. It didn't work. Now that is good news, because if a model doesn't work, we know that this model is not correct, right? Okay. We used a second model, a core shell model. Didn't work either. Okay. No, Jans Koff had another point, developed a fuzzy microgel, which kind of a dirty snowball model. Also didn't work. At that time, we got a little bit nervous, but finally we came up with a model that describes the data. I will come to that in a minute. It has A core shell type of structure has a sharp surface and has collapsed regions. That's the important point. It has collapsed regions. Now, just to convince you that this model is not too bad, this is the fit at scattering curves at 2 different times, and it really reproduces all these features that we have, especially when we look at this here, where we go for higher Q, where we have this many minima and maxima. So the model really describes the data. But the solution came only from computer simulations. And this is the computer simulation, again, from Roland Winkler's group. And what he could see in his simulations is that the collapse starts near the crosslinks, which makes sense because near the crosslinks, the density of segments is higher because we have this crosslink, right? So we have all these segments around. And if we go maybe back, you can see it stays porous. And due to the fact that it stays porous, because the collapse starts locally, the solvent can be expelled extremely fast. Yeah? Actually, we were not really able to capture the very first decay with the X-ray scattering. Now, so there is a 2-step collapse, and we wanted to see whether that depends on size. So Katja recently made much larger microgels, which were in the size of 100 microns, where we could do optical microscopy. And she also saw a 2-step process. So the collapse of these microgels is not very simple. It starts locally. It stays porous during the first process. So there is no skin, as what we can see from macroscopic gels. That is important to remember if people would like to use this for uptake and release properties. And, but then when the network becomes denser, it slows down tremendously and we have a slower second process. Okay, so much for the behavior in bulk. And I would like to switch gears and for a few minutes talk about microgels at interfaces. Now we know that small molecules absorb, especially when they are surfactants, absorb to oil water or air water interface and form a film, right? Particles can also absorb to interfaces, famous Pickering and Ramsden emulsions, depending on the wetting properties of these particles. They are either sitting in one of the 2 phases. And macromolecules also absorbed, and they can absorb in this kind of tail, train, and loop conformation of a chain. So that is different depending on the architecture or the structure of the material. So how do microgels behave? It has been shown first by Ton Guy that one can stabilize emulsions with these polynipalm microgels. And that is shown here. Now these are microgels where we used polynipalm and copolymerized them with methacrylic acid so that they are also pH dependent. And you can see that if we have extremely stable emulsion, so that emulsion is stable for years, but if you change the pH or if you change the temperature or if you change both temperature and pH, you can separate, you can break the emulsion and separate the emulsion. We at one point also added magnetic nanoparticles to it, and then you can control the stability. You can collect the droplets, or when you increase the heat by using an alternating magnetic field, you can also break the emulsion. So they are interfacially active. Just to show you that that is a little bit peculiar compared to other systems, we did a following experiment. We took a negatively charged microgels, so it had acidic groups copolymerized, and we took a different microgel, which is now positively charged with amine groups. And we used these microgels to prepare an emulsion, and these microgels to prepare an emulsion. And what Ting Ting did was said, okay, now we have microgels that have different charge. We have droplets, now oil droplets that have a different charge. Can we mix them? Yes, and we can mix them and they are stable. And this is also shown in this macrofluidic experiment, where from the one side we create droplets stabilized with a negatively charged microgel. From the other side we have the oppositely charged microgels. And you see that the droplets don't care. So despite the fact that the microgels have different charge and the droplets have different charge, they are stable. Now we can go, as these are pH dependent, we can go to a pH where either this one is not charged or this one is not charged. And this is shown here. This is at pH 4, where one of the systems is not charged. This is at pH 10, where the other one is not charged. And you see that in most cases, when the droplets meet, they coalesce. That shows that we can control the stability of these emulsions via the pH, but it also shows that it's not the charge that dominates the behavior of these microgels. Okay, good. Why is that interesting? Well, you could go for applications in biocatalysis where you would like to use an enzyme which is water soluble to transform or catalyze a reaction from an organic substrate or substrate which is soluble in an organic phase. And if you would like to do this in emulsion because you would like to have a large interface, then at the end you have the problem that you have the product in the droplets and you would like to break that emulsion. So for chemical engineering point of view, you would like to be able to switch between a stable emulsion and a broken emulsion in this process. And this can be done with the systems, and now our colleagues and the engineering department try to use this on a larger scale. Okay, but we were more interested in what's the structure of the microgels at these interfaces. So we have a nice collaboration with Lucio Isa from the ETH Zurich, who developed what is called freeze fracture shadow casting cryo scanning electron microscopy. We put the sample, the microgels, at an interface, break it, freeze it, break it, and then have a metal evaporation from the side. And he could show in this paper that if you have a rigid particle, you get a shadow from the metal evaporation here. And from that shadow, you can determine the contact angle of an individual particle. And when I saw this, I said, oh, we have to try this with our microgel. So we tried this, and this is what the result we got. And we did not see any shadow. Here we saw a shadow, but this is an ice crystal. Okay, so that shows that the technique worked. And what this shows us is that the microgels are objects that we can see. This size is much bigger than the size we have in solution. So what happens, they go to the interface, they deform, we could also say they spread at the interface, but they do not protrude much into the oil phase. And this is also what is shown in what we can see in computer simulations. This is a computer simulations from Igor Potemkin's group for two different types of cross-link density. And when they go to the interface, they spread or they deform. Okay, so that was the point where we said, now let's go for a Langmuir trough and look at that structure in more detail. So the idea is to put the microgels to the interface, squeeze them together, and then transfer them in a Langmuir blodgett type deposition on a solid substrate and image that with atomic force or scanning force microscopy. And this is a typical compression isotherm, surface pressure versus normalized area, that Karen and Steffen typically get for these type of microgels. Increased surface pressure, have a second increase here. Okay, now when we do the deposition on an AFM substrate and look at that in the AFM, we have compared that with electron microscopy images taken at different compressions, and we get the same images. So we are very confident that this deposition does not change the structure too much. Okay, so what do we see? When we are at very low surface pressure, we see the individual microgels. Now, if they are small enough, they form clusters for capillary interaction. But this is only for large microgels. Our microgels are typically small enough that you do not form a cluster. Okay. Now we're coming to the point where the surface pressure rises. And what we see is a wonderful 2D crystalline object organization. Wonderful large-scale crystal in 2D. Very nice order. When we increase the surface pressure, we decrease the area, we push them together, Okay, they move closer together. And then when we are getting into the plateau, oops, we see the occurrence of a second crystalline structure. We get a crystal-crystal phase transition between two different types of distances in the crystal. Both have an hexagonal order, but have distant interparticle distances. When we increase the surface pressure, when we compress them further, the second phase grows on the expense of the further one, and then finally we end up with a densely packed film that eventually fails if we compress it too much. And the reason for this is that in the beginning we have this core corona kind of structure for microgels with less crosslinks outside. And this is also something we have at the interface. And the first crystalline order is a corona-corona contact, and the second one is a core-core contact. So they interpenetrate more, and then the cores come into contact. So that is for what we see for the normal microgels. So what happens when we go to the ultra-low crosslink? You remember the ultra-low crosslinked also formed colloidal crystals in 3D, right? So we put them to the interface, and the surface, the compression isotherm looks very similar. Okay, when we are at high dilution, we see individual microgels. Again, this is the transformer as a deposited at a surface pressure of 0 here to the interface, to the solid substrate, and imaged with AFM. And now I will show you AFM images with increasing compression, such that means that the surface concentration goes up. We see them getting closer and closer, and now, oops, they're gone. Well, they're not gone, we don't see them anymore. What we see is an extremely homogeneous film. And that is shown here again. So we had these individual objects. What you cannot see is the scale here. This is 2 nanometers. So in the dry state, these ultra-low crosslink microgels are extremely flat. And when we increase the surface pressure, we push them together, we get a completely homogeneous film, like we would get from a polymer coating. We squeeze them further, then we start to see them again. So when we squeeze them sufficiently, as you can also see here, then these objects cannot fully interpenetrate, and they see that they have a crosslink, they are crosslinked and different objects. But at this intermediate surface coverage, we get a completely homogeneous film. So that would tell us that it's basically a polymer behavior. It's not a particle. So that shows that this flexibility and adaptivity of these microgels is really strange, such that we would call them a particle in bulk solution because they form colloidal crystals. But at 2D, we would call them a polymer that form a homogeneous coating. So you can imagine that that would allow us also to play now with coatings if we want to go for different types of applications. Now, this image is in the dry state. You might wonder, how do these ultra-low cross-linked microgels look in the liquid state when we add water? So we actually did liquid cell AFM, so we added water, so they were prepared under water. Now this is much more complicated for these soft objects, but here you see them, right? Okay, so at this high temperature, they should be collapsed. They are collapsed, we see objects. We go down with the temperature, we see them. We go further down, oh, we don't see them. Okay, now there are 2 possibilities. We don't see them because they are not there, or we don't see them because they are too soft. The only way of figuring out is going further down, we don't see them, and then heating up again. They are still there. So the microgels are here, that the force that is typically used for imaging is so high that we just go through the microgels and do not see them. Yeah? So we had to go for what people call the force volume measurements for spectroscopy. This is the image you've seen before. And when you look in detail into the force distance curves, so these are force distance curves where they plot the force as a function of sample to tip distance, only the substrate, and here we see an object. So there is something, and this is what you can try to see here. It's very extremely difficult, but if you really look into these force distance curves in more detail, this is the collapse state, This is the swollen state, and you can see this is the substrate. You go through it, but they are actually there. Yeah? This is for a normal microgel where this increase in force is much stronger, but better to be seen. So with this force spectroscopy, we can now investigate the stiffness here. And what we can do basically is Afm tomography. And when we do Afm tomography, we can look at the objects here. We can see them again. This is kind of a surface plot. But what more interesting is the tomography, where the color code gives us the stiffness. This is for a normal microgel. Soft outside, the further we go inside, the stiffer they are. And here, it's very stiff. For the ultra-low cross-linked, they are flat and extremely soft. They are softer than polymer brushes typically. So that again shows that these are really weird objects. These ultra-low cross-linked microgels are something in between a microgel particle and a polymer network. Let's say a polymer chain, I would rather say, very soft object. So coming to the end, I spoke mainly about fundamental aspects. This is what we do in physical chemistry. We are interested in these specific features of microgels. There are two reviews, one from our group and one from a collaboration with many other groups, where you can also learn a lot about many different types of applications. And with that, I would like to conclude. I hope I could convince you that microgels are simple but still complex, that it's fun working with them, that we can make complex structures. They can be hollow, they can have different shape, they collapse extremely fast. Even if they are very soft, they can form colloidal crystals, so they do behave like particles. But when we make them hollow or change the degree of cross-linking, we can control the softness. And hollow ones do not form crystals. They rather fill the cavity. So we can play with the architecture, and that leads to different physics. We can go for anisotropic microgels. And in 2D, they strongly deform when adsorbing to an interface. We can make stimuli-sensitive emulsions. We can get highly ordered structures. And we can have extremely soft coatings as well. Yeah? So we can play with the surface properties. We can use them for coating applications. And to put all this together, I think we have an object where both the flexibility, being swollen and soft, is important, but as well the persistence, meaning that we have a cross-linked object. It has a structural integrity. Now, you saw already the PhD students on the slides. These are the groups that we collaborate with. I especially thank the German taxpayers, because some part of their taxes goes to us via the German Science Foundation. And neutrons come from the ILL or from Munich, and ESRF gave the photons. And thank you very much for your kind attention, and I'm looking forward to a discussion.
Hi, Malte. Thank you so much for an amazing talk. You really replicated trying to give a real lecture, and I'm sorry that we weren't able to respond by being a real audience. So. But it felt very real. We have plenty of technical questions in the chat that I'll get onto, but could I ask you a very general question to start off with from myself? So for all of these different internal architectures that you're able to get, can you take us through some of the applications of these?
Yeah, so let's say one type of application would be that we combine the microgels with the catalytic site, catalytic center, and then we can do catalysis. And basically, this is a combination of homogeneous catalysis, because it's swollen by the solvent, so it's easily penetrable for the substrate. But on the other hand, you can collapse the object, you can filter it, so you also have a heterogeneous object. So this is, for instance, looked at in the group of André Pich in Aachen, Sonja Harris-Pavlis. That is one application. Then we have, this Sonderforschungsbereich. This is a collaborative research center, and where many different groups work together. And we have a group in medical school, and the idea is to fight diarrhea, and by having microgels that can capture toxins that would attack the colon. And that actually works. So they actually get these microgels. They have an active site as a sugar moiety that binds the sugar motif. The mice swell this, and then it goes into the colon and does its job. And then the last point is, in terms of large-scale application, would be the stimuli-sensitive emulsions. There we have a collaboration with a group who is really doing this for a pilot plant application. Okay, so these are many different fields. People go into sensors. We have a collaboration on sensing and things like this.
Cool. Thank you so much. So I think what I'll do is I'll read out all the questions in the chat from my colleagues who have asked them. And actually, so I propose that to those who've asked a question or who think of a new question, if you would like to raise your hand and ask it in person, then we can do that as well. So the first question is from my colleague Martin Trassler, who asks, does the viscosity of the aqueous microgel system correlate with the particle size determined from light scattering?
Yes, for spherical objects, the viscosity depends on the volume fraction. And so when we change the temperature, we change the size and the volume fraction, and that perfectly fits to hard spheres until we get to dense packing. Beyond dense packing, it's different from hard spheres, obviously, because we can go to higher packing. And that's also, then the rheology is very rich, becomes also polymer-like, glassy-like, but in the dilutes, let's say up to 50% volume fraction, like hard spheres. Okay. Okay, Martin, if you would like to have a follow-up chat, then raise your hand and we could come back to you. Next question from Paul Larkham. So a specific question, I believe, about one of the slides that you showed. So in the core shell microgel with methacrylamide, how do you explain that the swelling starts at 40 degrees rather than 45? This is roughly halfway between the LCSTs for the two polymers. Okay, so that depends a little bit on, basically it's a competition between the core that wants to expand already and the shell does not yet want to expand. So there's competition. That depends a little bit also on the crosslink densities, whether the shell is able to constrain the core sufficiently, or whether it has to expand already a little bit. So that depends on the mass ratio and depends on the crosslink density of core and shell. So we can play around that. Okay. And is there any evidence for a distribution of crosslinks away from the center of the particle? So Paul Larkham says, I know a few years ago people speculated that the center may be more cross-linked than the edges. So basically our scattering profile from the normal microgels, when we have them in the swollen state, we cannot fit them with homogeneous sphere models. So that shows that the density is higher in the center as compared to the outside. And that fits to the reaction kinetics, because that is known that the crosslinker reacts faster. We have looked at this also in collaboration with Dominic Wöll, where they used a second crosslinker that we can really look at that in the super resolution fluorescence microscopy. This goes for larger microgels, and that also is shows that we have this variation of crosslink density. Yeah. Okay. Paul says thanks. Okay. And you're welcome. I have a question from João Cabral, who says about the photonic crystals. Presumably one can shift optical properties with external fields, for example, thermal or chemical. And then a follow-up question also with biodispersed microgels, they segregate and mix crystalline systems or no? Okay, maybe for the first question, yes. So actually we have done one experiment in neutrons where we either changed the concentration to get this crystallization going. When we change the concentration, we have more and more objects. So we get a structure factor peak, and that shifts with concentration because we have more object, we have a different distance. When we do the same experiment at a constant concentration but different temperature, then basically we also change the effective volume fraction, because when we go down, they swell. But now the number density is constant, and then the structure factor peak does not change because it's always the same distance. And if you go for colloidal crystals or applications, for instance, Matthias Karg, he does a very nice job. He takes a gold nanoparticle as a small core and then prepares polyniper microgel shell. And then you get also colloidal crystals, but then of course you also have this plasmonic properties. And you can also do the same trick as we did here, but have much stronger optical effects. And the second question I forgot, sorry.
So with biodispersed microgels, do they segregate in mixed crystalline systems?
For the, I guess that goes for the 2D system. Actually, we don't really know yet. I discussed that with some theoreticians, and they say, well, if you have an interaction potential that has a shoulder, that could lead to this kind of phase separation, let's say these crystal state phase transitions. And now we know that we have this core corona structure also at the interface. So we would expect that the interaction potential is soft in the beginning and becomes steeper. So there should be a shoulder in this potential. But it's still, I would say, an open, not fully understood point why they have this transition.
So what exciting plans have you got going forward with this work?
Oh. So we are now going more and more for the anisotropic ones. We have been looking at the anisotropic ones at interfaces. You could imagine now that they form colloidal crystal, liquid crystals, 2D liquid crystals. Again, different as compared to really the ordering, because you have anisotropy in different ways in terms of structure and things. We have now been making much larger hollow microgels where we go into capsules and they do show bending. They do not, though you could imagine if you have a capsule, it could shrink or it could bend. And the small ones I showed you collapse. The large ones, I did not show you, they're very new data, they bend. So there is a size dependence in these properties, where they also really, especially the capsules, show very different things. And we would like to tune the possibilities for charged microgels. We have charged hollow microgels, and we have good indications that we can lock charged molecules inside. So, different things to explore.
And are you going to continue the experiments with the microfluidics? Which looked very fun, actually. I
mean, for the emulsions, yes, they are fun for emulsions. Typically, the peculiar behavior of microgels comes from the internal structure, that you have this fuzzy surface. And that plays a major role when they are small. If you go, let's say, to 10 microns or 100 microns, then that fuzziness is small compared to the entire particle. So I personally believe that the small ones are really interesting ones, but they are more difficult to observe in microscopy. But with all these Newton scattering techniques, I think we can get even more information on this. So.
Incredible. I have one for myself, another question about, so you showed the long equation towards the start of your presentation for modeling purposes, right? Which parameter is the most elusive, and how do you optimize so many parameters? Because I mean, so I don't work in this field, but we also have many models where there are so many unknowns that, like you said, you can fit, anything, and you have to constrain all the parameters to actually estimate ones that are meaningful. But there's still a lot of uncertainty in the end. So I was wondering how you get around that issue.
Yeah, maybe I show one example again. What is really, let's say, when we have these types of scattering curves, the position of the minima is very sensitive. And so the most important parameter that we typically have is the size plus what we call the fuzziness of the surface. And these are different length scale. Let's say the size is something like 100 or 200 nanometers, and the fuzziness is something like 50 nanometers. And that allows us And let's say when we change with the parameters, some parameters affect the behavior in the front and here at that part of the curve, whereas other parameters are more important here.
Mm-hmm.
And that allows us to distinguish between different models because they might be able to fit let's say this part of the curve, but not the other part.
Uh-huh.
And so when I had this system on the too many plots, huh? This one here, let's say if I go really, so we had many models that were able to, let's say, fit half of the scattering curve.
Mm-hmm.
But if you look at this, for instance, you have now a second maximum, a maximum which is higher than the previous one.
Mm-hmm.
That gives you an idea that there is a specific length scale that is relevant.
Mm-hmm.
And then if you have a model, let's say, okay, we have now this collapsed region, maybe that's the size of the collapsed regions. And when you vary that parameter, it will affect the scattering curve here, but not here. And that allows you to distinguish between different parameter sets.
Okay, so basically you're able to simplify the model for the different regions of the response, and then you put the whole thing together to get one curve. Mm-hmm.
Yeah, but to be honest, the time from beam time to paper in this case was 6 years. It was a damn fast experiment. It took us long to figure that out. But it worked at the end.
Yeah, I'm familiar with it's answering why that takes
yeah.
the longest. Okay, oh, we have another question in the chat while we were talking. So could you please comment further on the mechanism of colloidal stability of suspensions of the microgels when the outer layer whole microgel is collapsed? Does charge now play a role, or are they still sterically stabilized? Mm-hmm.
No, so that's really a charge stabilization. So the initiator we use is potassium persulfate. So it gives us charge groups. And this is also the reason why during the synthesis of the precipitation polymerization, they are stable. Now, when we purify all the system, and so basically these few charges sitting at the surface during the polymerization are sufficient to stabilize them. Mm-hmm. Now, when we add salt, they flocculate. And if we, for instance, add a surfactant during the polymerization to make them small, and then remove the surfactant afterwards, then these systems are less stable at high temperature, and then very small amounts of salt affect this, and then they flocculate. So it's basically a charge stabilization in the collapse state that makes them stable. Mm-hmm.
Okay. I think that's all the questions in the chat. This whole discussion, so it reminds me of the problem we have in 3D printing, 3D inkjet printing that we do in the lab, but we're trying to 3D print just metals. And you can never get just one size of particle. There's always secondary and tertiary particle size distributions. So getting the viscosity right for the printing, as well as keeping the particles separated is very challenging, and it's not even so complicated as what you're working on.
So when we do the Correlate particles, we also have to face problems with secondary nucleation. So we really have to be careful doing this in the right concentration, or then doing the separation correctly. Yeah, the purification. Yeah.
Okay. Well, thank you so much for joining us today. I think that's all the questions, but plus I think you could do with this short break before you meet some of my colleagues in another meeting. So I'd like to thank you on behalf of the whole department for joining us today to give this fascinating talk. And I think it was interesting to a great many colleagues today.
Yeah, thank you very much.